Welcome students. In our previous lectures, if you remember, we have discussed the axial force diagram, shear force diagram and bending moment diagram for simply supported beams and for cantilever beams, that is for determinate structure. Let us extend our discussions on axial force diagram, shear force diagram and bending moment diagram for simply supported portal frame. And let me tell you, one more video link is provided in the description of this video, where you can go to the for drawing axial force diagram for simply supported portal frame. So let us imagine that this is the portal frame. Let's have the portal frame. Simply supported means this support must be a hinge support, and this support must be a roller support. Let us say this beam BC, I'll name it. This beam BC is of length 4 meters. This is B, this is C, this is end A, and this is end D. Let us say there is a point load at this of 10 kilonewton, and there is a UDL, uniformly distributed load, of the intensity 4 kilonewton per meter. These are the two loads, and yes, let us say these are the loads, and let us assume, or let us say given that this length AB and CD is 5 meters. 5 meters. So simple frame, simple portal frame, where we need to draw axial force diagram, shear force diagram and bending moment diagram. So the first step is determination of the support reaction. Step 1 is determination of support reaction. So I'll insert a chat box. Step 1 is determination of support reaction. Determination of support reactions. Support reactions. Step 1 is determination of support reactions. Uh, I'll change the color. Determination of support reactions. So the how many support reactions are possible? The support reactions possible for the hinge support, we know there are two reactions possible. Let's call this reaction as horizontal reaction at A. Let's call this reaction as vertical reaction at A. And let's call at roller support only one reaction perpendicular to the roller is possible. That is, let's call this reaction as VD. So there are three support reactions and there are three equations of equilibrium. So we know very well that we can determine these support reactions using equations of equilibrium alone, and that is why this is the determinate structure. So I will write the first equation, summation of forces in x direction, that is equal to 0. All the forces acting towards right hand side are positive. This is my assumption. So I will go on scanning the structure from A to D. So what are the forces at A which are acting to the right hand side or which are acting in x direction? This HA is the force which is acting in x direction. Let me again revise that this is my x direction, positive x direction. This is my positive y direction. And Z plane is the plane which is entering into the screen. So HA is the force acting in x direction. It is acting towards right. This means it is acting in a positive x direction. So I am writing HA is my positive force, summation of forces in x direction in 0. From A to B, I will scan. At B, there is a load of 10 kilonewton which is acting in the right hand side. So that is also positive according to my sign convention. So HA plus 10. And then from B to C, there is no load. From C to D, there is no load acting in x direction. So HA plus 10 is equal to 0. This is my first reaction. So first equation, therefore, I will write HA is equal to minus 10. HA is equal to minus 10 kilonewton. What does this minus sign indicates? Minus sign indicates that my assumed direction for the reaction was wrong. This reaction must have been acting in opposite direction. So I will draw it later. I will draw the structure later. HA will must have been acting. HA minus 10 This means this reaction HA must have been acting towards left. This HA is equal to 10 kilonewton towards left. My HA assumed was right hand side, acting towards right hand side, but it comes out to be negative. This means the actual reaction at HA should have been acting to the left hand side. My assumed direction is wrong. Now let's calculate for summation of forces in y direction is equal to 0. It should be a methodic approach, it should be a step by step approach, so that there are no chances of committing any mistake. So I will scan again from A. So force acting in a y direction is VA acting upwards. There is no other force between A and B. This 4 kilonewton per meter is the force which is acting in y direction, but it is acting downwards. So plus VA is acting upwards, that is why plus VA minus this 4 kilonewton per meter acting for a distance of 4 meter. So 4 into 4, that is acting downwards, plus this VD is also acting in positive y direction. So plus VD is equal to 0. Therefore, I will write VA plus VD is equal to 16. 4 plus 4, 4 into 4 is 16. So this is my second equation. I still need to find out the value of VA and VD. I have not got these two separate values. Now I will apply the third equation. Third equation of equilibrium for two dimension is summation of moment acting at any joint A is equal to 0. My sign convention is I will take clockwise moments as positive. Now look at this. Look at this. The moment created by HA at A is 0 because HA is passing through A. There is no perpendicular distance between HA and A. The moment created by the force VA at A is 0 because VA is passing through A. There is no perpendicular distance between VA and A. Now, what is the moment created by this 10 kilonewton at A? This 10 into perpendicular distance is 5. So 10 into 5, and it is acting in a clockwise direction. If we consider this as hinged, if we suspend some cantilever from here, so this 10 kilonewton force will rotate this cantilever about A in a clockwise direction. So 10 into 5 clockwise. So I am going to write 10 into 5, that is the moment created by 10 kilonewton load. Since it is clockwise, I am writing it positive. Now another force is this 4 kilonewton per meter. This 4 kilonewton per meter acting for a distance of 4 meter. So that is 4 into 4, 16 kilonewton meter, and this 16 kilonewton meter is supposed to be concentrated at center of this, that is the perpendicular distance between these two is 2 meters. Perpendicular distance is 2 meter, and it is again, if I say how is it acting, if I say it is acting like this and this is the suspension, then it will rotate in a clockwise direction. So that is 16 into 2, so 4 into 4 into 2, that is also acting in a clockwise direction. So plus 4 into 4, that is the load, and the perpendicular distance between the load and point A, this is the point of application of the perpendicular point of application of the uniformly distributed load at the center of BC, and the center of BC is 2 meters from A, and it will create a clockwise moment at A, that is by plus 4 into 4 into 2. Now there is one more force acting on the structure, that is reaction VD. Now see, VD and A are 4 meters apart. The perpendicular distance between the force VD and A is 4 meters, and if I suspend it and if I allow the VD to act, this VD will create an anticlockwise moment at A. In that case, I will write minus VD into 4, minus VD into 4 is equal to 0. Therefore, I will calculate VD is equal to, this is 50, and 4 into 4 into 2, so that is a 10 into 5. VD is 10 into 5 plus 4 into 4 into 2 divided by 4. So I will cancel this 4 with 2.5 over here, and I will cancel this 4 with 4. So 2.5 into 5 and 4 it plus 4 into 2, 8. So 2.5 into 5 plus 4 into 8. Therefore VD is equal to, therefore VD is equal to 2.5 into 5, 12.5 plus 8, that is 20.5. So VD is equal to 20.5 kilonewton. It is positive. This means assumed direction of VD upwards is all right. And now I got the equation VA plus VD equal to 16. Therefore, if I put it, I will get VA is equal to minus 4.5 kilonewton. This means VA should be acting 4.5 kilonewton downwards. My assumed direction for VA was upwards. Since it is coming out to be negative, this means VA should be acting minus 4.5 kilonewton downwards. I am again drawing the structure with the support reactions. My support reactions were like this. I will indicate the structure with support reaction. These are the applied forces, 4 kilonewton per meter. This is the applied force. This is 10 kilonewton to be simple. Simple values B, C, A and D. I got the reaction VA minus 4.5. Minus 4.5 means assumed direction was wrong. It should have been acting in the negative direction, that is minus 4.5. Comes out to be minus 10. This means assumed direction was wrong. So HA is plus 10. And VD I got is 20.5 positive. This means assumed direction was right. So 20.5 kilonewton, that is upwards. So these are my support reactions. So my first step for finding out support reaction is over. Now I will go to my second step. The second step is determination of, step 2 is determination of, I'll just copy it. And my second step is drawing of axial force diagram. Step 2 is axial force diagram. If I draw the correct axial force diagram, step 2 is axial force diagram. Axial force diagram. So if I draw the correct axial force diagram, I know a lot of my problems are going to get solved. So I will start drawing the axial force diagram from D to C. So I will draw the axial force diagram first of D to C. So I will draw it for D and C. So D end is over here, C end is there. I am drawing axial force diagram. I am showing the implied forces first. So the first force, that was the reaction at D, is 20.5 kilonewton. We cannot change it, we cannot alter it. 20.5 kilonewton. This is point D, this is point C, and the distance is 5 meters. There is no other force acting on CD. There is no other force acting on CD. Now I know each axial force diagram is a balanced diagram. This is axial force diagram. Each member and each joint is in balanced state. So it should follow all the equations of equilibrium. So if the upward force is 20.5, I have to adjust the force. All adjustments I need to do is at C, because I have broken joint C. Let us say I have taken a break at joint C. I have broken the structure in the part DC and BC. I have broken joint C. So all the adjustments are to be made at joint C. So I have broken joint C, and I will just adjust it by applying equal and opposite forces so that the structure is balanced. So summation of forces in y direction is equal to 0. So it must be acting, C must be acting downwards 20.5 kilonewton. Since there is no force acting in x direction, so balanced force is 0 kilonewton acting at C. We did not show it at a later stage, since this is the first numerical we are showing it. So balance force is 0 kilonewton at this. And then what is the moment? There is no moment acting at joint C. This 20.5 kilonewton will not create any moment at C, because principle of extensibility of force, that is one of the axioms of mechanics. This force will pass through C. There is no perpendicular distance between this force and C, and that is why no moment will be created at C. So we don't need to balance it with any moment. But since this is our first example, let's balance this with 0 kilonewton meter anti-clockwise moment. It does not carry any moment. 0 kilonewton meter anti-clockwise or clockwise, it does not carry any meaning. But since this is our first example, we are just for your clear concept, I am just indicating. So I have balanced this joint, I have balanced this member CD. Now we can see member CD is statically in equilibrium, is in static equilibrium. Member CD is in static equilibrium. Summation of forces in x direction at member CD is 0. Summation of forces in y direction in member CD is 0. And summation of moments acting on member CD is 0. So that member is in static equilibrium. Every member, every joint should be in static equilibrium. That is the basic concept of drawing axial force diagram. So member CD is in static equilibrium. Now I have balanced member CD. I will draw member BC. Now this is B and this is C, and it is acted upon by the load 4 kilonewton per meter, and the distance BC is 4 meters. This is what is given. Now I have to balance, since this joint C and this joint C in the member BC and joint C in the member CD are the same joints. So I need to balance joint C by applying equal and opposite forces that were balanced at C, that were required to balance C in the member CD. So this 0 kilonewton towards left will be acting as 0 kilonewton towards right. This 20.5 acting downwards will be represented as 20.5 kilonewton acting upwards, and then this 0 kilonewton meter anti-clockwise will be transferred as 0 kilonewton meter clockwise. My friends, remember the 0 kilonewton and 0 kilonewton meter need not be transferred. Since this is the first numerical we are solving, I am just indicating it for your convenience. So joint C is also balanced. So whatever are the balanced forces on joint C in the portion CD, equal and opposite must be transferred to joint C in the member BC. Now joint C is balanced. Here we have balanced the member CD. Here we have balanced joint C. Now we need to balance the member BC. Now we cannot touch, we cannot do anything at C. C is already balanced. We whatever balance we need to do is at joint B. So let's balance joint B. So summation of forces in x direction, there is no force acting in x direction. So this is equal to 0 kilonewton. Now summation of forces in y direction, 20.5 upwards, and is 4 into 4, 16 kilonewton downwards. So 16 kilonewton meter downwards, 16 kilonewton downwards, 20.5 upwards. So this must be balanced by a downward force of 4.5 kilonewton. I add it, 4.5 kilonewton downwards plus 4 into 4, 16 downwards. That is 20.5 kilonewton downwards and 20.5 kilonewton upwards. So summation of forces in y direction is also balanced. Now what is the acting moment at B? Acting moment at B is 20.5 into 4. 20.5 into 4, that is 82 kilonewton meter, that is acting in anti-clockwise direction. To balance it, there must be a balancing moment of 82 kilonewton meter acting in clockwise direction. At the same time, this 4 into 4 into 2, that is 4 into 4 into 2, 4 into 4, 16, 16 into 2, that is 32. 32 kilonewton meter is also acting in a clockwise direction. So to balance it, there must be 32 kilonewton meter acting in anti-clockwise direction. So net moment acting, net balance moment, it is 82 kilonewton meter is balanced to be acting clockwise, and 32 kilonewton meter is the balance to be acting anti-clockwise. So the net balance is 50 kilonewton meter acting in clockwise direction. So if I apply the 50 kilonewton meter in clockwise direction, that will be balanced 50 kilonewton meter, because the clockwise moment is 32, only 4 into 4 into 2, and anti-clockwise moment is 82. So if I add 50 kilonewton meter clockwise, in that case 82 anti-clockwise and 50, this 50 plus this 4 into 4 into 2, 32, that is 50 plus 32, 50, 82 kilonewton meter clockwise. Anti-clockwise 82, clockwise 82. This structure is balanced. This member BC is balanced. So that is a balanced member BC. Now you must have judged it right. I need to balance member AB. I need to balance member AB. Now look at my friends. This is 10 kilonewton, which is the given load acting at joint B. Now the rule is you should take 10 kilonewton into consideration acting either in member AB or in member BC. It will not make any difference if you take it in either of the members. You cannot take it acting in both the members. This is the golden rule you must remember. This 10 kilonewton load must have been taken into consideration either in member AB or in member BC. You cannot take it into consideration for both AB and BC. It will multiply the error. So I have considered this member, this 10 kilonewton acting on the member AB. So I am showing the forces that are acting on the structure. This is 10 kilonewton, which is already acting on the structure. And then I know the reactions. This 10 kilonewton and 4.5 kilonewton are the reactions that are already acting on it. So 10 kilonewton and 4.5 kilonewton acting downwards are already the reactions at A. This is A, this is B, and this length is 5 meters. That I know. So these are the acting forces which I don't have the permission to change. And from B, this joint B in the member BC to this joint B in the member AC, I will transfer the balance forces in equal and opposite direction. This 0 kilonewton acting towards right will be transferred as 0 kilonewton acting towards left, acting towards right. Then this 4.5 kilonewton acting downwards will be transferred as 4.5 kilonewton acting upwards, and this 50 kilonewton meter clockwise will be transferred as 50 kilonewton meter acting anti-clockwise. So three forces which are balanced in the portion BC are transferred equal and opposite in the member AB. Now look at this. Now I will get a check at the end whether member AB is already statically balanced. Let's compare member AB. Summation of forces in x direction, this is acting in towards right, this is acting towards left. Summation of forces in x direction is already equal to 0. Summation of forces in y direction, this 4.5 kilonewton acting upwards and this 4.5 kilonewton reaction acting downwards, these are balanced, so that is equal to 0. And now look at the moment at A. This 10 into 5, 50 clockwise is balanced by 50 anti-clockwise. Or even at B, 10 into 5, 50 clockwise is balanced by 50 anti-clockwise. So this is correct. This we can say that member AB is already balanced. So this is correct axial force diagram of the frame ABCD. Axial force diagram of the frame ABCD. Now my friends, the general sign convention is that the observer is inside the frame. Observer is always inside the frame. So the observer will look AB portion from this view, BC portion from this view, and CD portion from this view. This is very important because if we consider the observer standing outside the frame, our bending moment sign conventions will change, and instead of positive bending moment, we may get negative bending moment. So observer is inside the frame, so AB, BC, and CD. So once the free body axial force diagram is ready, we can plot shear force diagram and we can plot bending moment diagram. So step 2 is over. Now we'll go for step 3, that is axial force diagram. We'll go for step 3, that is step 3 is shear force diagram. Axial force diagram is over. Step 3 is this free body diagram. Step 3 is axial force diagram. Axial force diagram. Step 3 is axial force diagram. Let me correct. Step 2 was free body diagram, not axial force diagram. So step 2 was free body diagram. This is free body diagram. Step 2 is free body diagram. Step 3 is axial force diagram. I am plotting AB, BC, and CD, and I am looking at axial force diagram. What are the axial forces in the members AB, BC, and CD? This is AB, this is BC, and this is CD. BC and CD, and I will plot the axial force diagram of AB, BC, and CD. Now look at the axial force. This is 4.5 kilonewton. It is creating tension in the member AB. This 4.5 kilonewton upwards, this 4.5 kilonewton downwards. Axial force is the force which is acting perpendicular, which is acting parallel to the axis of the member. So let me correct it. This is free body diagram. This is FBD, not AFD. This is free body diagram. Okay. Now we are drawing axial force diagram. So for the member AB, this 4.5 kilonewton is axial force which is tensile in nature, and my sign conventions, if I refer my first lecture, sign conventions that tensile forces are positive. So 4.5 kilonewton, 4.5 kilonewton are axial forces which are tensile from A to B, and they are positive. Look at the axial force in BC. Axial force in BC 0 kilonewton and 0 kilonewton. There is no axial force in BC. So axial force in BC 0. So that is 0 kilonewton. Same is the case with axial force in CD. Look at it. This 20.5 kilonewton axial force is the force which is acting parallel to the axis of the member. 20.5 kilonewton and 20.5 kilonewton, but both of them are creating compression, and my sign convention is compression. I take negative. So this is 20.5 kilonewton. This I will indicate by negative sign. This is 20.5 kilonewton and this is 20.5 kilonewton. So both the axial forces are negative. So this is my axial force diagram. My friends, once you draw the free body diagram, everything becomes very simple. So this is axial force diagram. Now let's solve for shear force diagram. Let's go. That's next step is drawing shear force diagram. Step 4 is drawing shear force diagram. So I'm copying it and pasting it over here. Drawing step 4 is shear force diagram. Step 4 is shear force diagram. Look at it. Once you draw the free body diagram, everything becomes very simple. So again, for shear force diagram, I am plotting member AB or member BC and member CD over here. Okay, AB, BC, CD, I am plotting for shear force diagram. AB, BC and CD, these are the forces in shear force diagram. Now look at the axial force diagram. For shear force is the force which is perpendicular to the axis of the member. So let us take a section XX at a distance x. I am looking the frame from inside. So this is my view to look at member AB. Now look at this. Left hand side acting upwards 10 kilonewton. Left upwards is positive. Right downwards is also positive. So it is a positive 10 kilonewton shear force acting throughout the member AB. So I am drawing shear force diagram as positive 10 kilonewtons act throughout the member AB. Positive 10 kilonewtons. It is not changing en route. It is not changing in between. So 10 kilonewton at A and positive 10 kilonewton at B. Look at this. I have my sign conventions for shear force. Left upwards is positive. Right downwards is positive. So this is my positive shear force. Now I am looking the frame BC from this angle. I am looking the frame BC from this angle. So let's again consider a section XX at a distance x from this B. Now, what is the shear force? If I write the shear force equation, I am writing it over here. Shear force at XX. Shear force at X. Now, limit of the section is 0 less than or equal to X less than or equal to 4 meters, because this section varies from 0 to 4. When the section is at B, X is equal to 0. When the section is at C, X is equal to 4. So I am writing shear force equation XX. So this is 4.5. Left hand side downwards, that is negative. So minus 4.5 is the shear force. And then this 4 into X, that is also left hand side acting downwards, negative. So at shear force at B, when x is equal to 0, the section is at B. Shear force at B is minus 4.5 kilonewton. And shear force at C, when x is equal to 4, 4 into 4, 16, minus 16 minus 4.5, that is minus 20.5 kilonewton. Look at this. Right of section upwards, left of section downwards, both are negative. So we are getting the value both negative, minus 4.5 and minus 20.5. So this is minus 4.5 kilonewton. I am indicating like this, and minus 20.5 I am indicating like this. Now my friends, look at this. How to connect these 2 points? Look at the equation of shear force. Equation of the shear force is minus 4.5 minus 4x. It is the equation varying with single degree of x. This means they must be connected by a straight line, because single degree equation is equation of a straight line. Both are negative. 4.5 kilonewton at B and 20.5 kilonewton at C, and both should be connected by a straight line. This is the equation of a straight line, because shear force equation is equation of a straight line. Now look at this shear force acting in the section CD. I am taking any section XX at a distance x. Needless to say that I am observing the frame from inside like this. That's I am observer inside and observing C to D like this. So left hand side 0 kilonewton, right hand side 0 kilonewton. Shear force in the section CD is 0 kilonewton. So I am indicating it 0. There is no shear force in the section CD. So shear force diagram for it is equal to 0. So this is shear force diagram. Friends, I have already emphasized upon this stress upon the correct axial force diagram. Drawing correct axial force diagram will give you half the battle won. Now the last step, step 5, is bending moment diagram. Last is bending moment diagram. BMD, bending moment diagram, BMD. So last step, bending moment diagram. Again, I will go to this axial force, free body diagram, and look at this. Now, I am using some different color from the palette. I am using this orange color for bending moment diagram. So I'm plotting the bending moment diagram over here. Bending moment, for bending moment diagram also I'm plotting AB, BC and CD. AB, BC and CD, I have plotted it. Now look at this. What is the bending moment? Bending moment is external unbalanced moment at the section XX. So bending moment at the section XX, if I take, this is 10 into X, 10 into X, left hand side of the section acting clockwise, that is positive because it is sagging. So 10 into X. So bending moment in the section is 10 into X. Limit of the section is 0, less than or equal to X, less than or equal to 5. There can be one single section between A and B because load is not changing. So what is bending moment at A when X is equal to 0? The section is at A. When X is equal to 5, the section is at B. Bending moment at A, if I put X is equal to 0, bending moment will be equal to 0. And bending moment at B will be equal to, if I put X is equal to 5, it will be 10 into 5, that is 50 kilonewton meter. That is the bending moment at B. Now my friends, look at this 50 kilonewton meter acting to the right of the section anti-clockwise. Right anti-clockwise is positive. Our value from the equation is also positive. So 0 at A and 50 at B, this 50 kilonewton meter positive bending moment at B. And now how to connect these 2 points? The equation contains single degree of X. The maximum degree of the equation is single degree, and that is why these 2 points are to be connected using a straight line. So this is 0 and 50 positive, that is bending moment diagram. So 0 and 50, 50 kilonewton meter. Now look at point BC. I am looking it from inside. This 50 kilonewton for BC, left of the section acting clockwise, that is positive. And look at the right of the section, it is 0 kilonewton meter. So 50 positive and 0 is negative. So I am plotting these 2 points, 50 kilonewton meter acting positive. My friends, this B and this B are same. So bending moments must be same, 50, and here it is 0 kilonewton meter acting at point C. So 0 kilonewton meter. How to connect these 2 points? How to connect these 2 points? Just like we have written the shear force equation, I will write bending moment equation for this. Bending moment at XX. This is 50, that is clockwise to the left, that is sagging, that is positive. 50 minus this 4.5 into X, that is anti-clockwise to the left, that is hogging, that is negative. And this 4 into X by 2, that is minus 4 into X by 2. Limit of the section is 0, less than or equal to X, less than or equal to 4 meters. If I put X equal to 0, that is bending moment at B is equal to 50. If I put X equal to 4, that is bending moment at C, put X equal to 4, 4.5 into 4 minus 2 into 4 square, you will get bending moment at C is equal to 0 kilonewton meter. 0 kilonewton meter. 50 minus this minus 2x square. So that is equal to 0. 4.5 into 4, 4 4 are 16 and 0.5 4 are 2, 18. 18 and 2 into 4 square, that is 2 into 4 square, 16 into 2, 32. 32 plus 18, that is 50. 50, 50 minus 50 plus 50, that is 0 kilonewton. So this is 0 kilonewton meter. Now what is the degree of the equation? The degree of the equation is second degree equation. It's a curve. So let us plot, let us say that there is some midpoint D which is at a distance 2 meter from B, and let us find out the bending moment at D. So bending moment at D, because of the lack of space, I am finding out it over here. I am just putting X equal to 2. So 50 minus 4.5 into 2, that is 9, minus 2x square. 2 squares are 4 into 2, that is 8. So that comes out to be 50 minus 9 minus 8, that comes out to be 9 and 8 17. 15 minus 17, that comes out to be 33 kilonewton meter acting at midpoint if I use the equation. Now if I connect it by a straight line, if I connect it by a straight line, 50 and 0, the midpoint should be midpoint should have been, the midpoint should have been 25. Midpoint should have been 25. At D, it should have been 25. So 4.5 into 2, that is 9, and 2 into x square, 2 square, 4 into 2, 18, 33. So it must be acting a concave parabola. So this must be a concave parabola like this. This must be a concave parabola like this. Must be acting like this. And then what is the bending moment in the portion CD? C, bending moment at C 0, bending moment at D 0. There is nothing that will create the moment. Therefore, at C is also equal to 0. D is also equal to 0. So CD, the bending moment is 0. This is positive. This is positive. So this is bending moment diagram. Other one is shear force diagram. And I can club these three together. This is fragmented I have drawn, and this is axial force diagram and free body diagram. So friends, it was very important to draw correct free body diagram. For a free body diagram, balance a member, balance a joint, balance the member, balance the joint, and then balance the member. This is the procedure we follow for free body diagram. Observer is always inside the frame, and we draw the correct reactions, and we plot axial force diagram, shear force diagram, and bending moment diagram for a simply supported portal frame. I hope you have understood it. For any difficulty, for any problem, please don't forget to mention your problem in the comment section of this. I will just go through it, and I will try to solve. I will be more than happy to solve that particular difficulty. Thank you. Thank you very much.